First of all, thank you for the opportunity. It's a pleasure for me to be here. I will present an example of testing of a photovoltaic power plant in EMTP in compliance with the Mexican grid code. First, the content of the presentation is modeling and simulation testing of photovoltaic plants, details of the modeling, and also point number 3, 4, 5, and 6 are the results of the tests. Also point 7. First of all, at the company, we specialize in the development of mathematical models with the objective of evaluating the behavior of the different power plants. This specific case, we will present photovoltaic power plant. This is a requirement that all the power plants that pretends to interconnect to the system has to reach in order to prove that the power plant will be prepared to interconnect to the system. I mean, before the real tests are carried out, you have to present the simulations of the behavior of the power plant. First, the power plant is modeled, and in compliance with the Mexican grid code, we have to perform some tests. The first one, the test that we have to perform are the active power control test, reactive power control test, power factor test, and voltage control test. Of course, in order to be able to perform this test, we have to initialize the model with the objective of simulate the behavior of the plant in a steady state, and then we can apply the test. And also we have to analyze the power plant behavior under frequency deviations. I mean, how the power plant will help the system to regulate the high and low frequencies according to the requirements established in the Mexican grid code. Well, for the modeling, this is an example of a photovoltaic power plant. This is a short example where we present the interconnection of the plant to the system. So we have to represent the system with an equivalent, and also we have to send the power plant controller. This is the key point of the of the instructions that the power plant controller will give the instructions to the plant to move the values of the active power, or frequency. But in order to have accurate results, we have to model everything in detail. I mean, for example, the transformers, the lines, all these small details have to be very precise, because sometimes if you don't have the values, the parameters, you can obtain different values, and the test will not be accurate, because after we simulate this EMTP, this same test will be performed for the plant in real life. I mean, so if we don't model every single element with the detail, with the correct detail, we cannot obtain accurate results. For example, well, in another hand, One problem that we have already with this kind of simulations is that for a precise simulation, we have to use a small integration step, but but we have to simulate around 10 to 20 seconds. So we will spend a long time simulating, and we have to perform not just one simulation, we have to simulate different scenarios. So that's a huge challenge that we already faced, because sometimes we lose a lot of time just simulating, and we try to use a larger time step integration, but results change a lot. So we have to keep in that time step. For this specific case, we use 2 microseconds to simulate around 20 seconds. So every simulation we perform took around 8 hours just to obtain one result. And if the results are not well, we have to re-simulate again and again, and we can lose a lot of time. That's one of the big challenges that we already faced. What else? Okay, I think that's a big deal we have until here. In general, this is a model that we present to NASA ask. I mean, before the interconnection of the central, we have to present these results. And then after the interconnection of the central, after the real test, we have to tune these models according to the real results. That's the next step. In this presentation, I will present only the first step before the interconnection of the central. So let's go to the first example. The active power control test is performed, in this case, for example, 20 seconds with steps of 5 seconds and 26 megawatts. So we have these 3 set points to reach. If you can see, we reach the value in 3 seconds. According to the Mexican grid code, we have to reach at least 90% of the value. So in this case, the active power control test is having good results. And for example, we reach almost the desired value in 3 seconds. That's a good result, but also during the commissioning test, the active set point is applied from 100% to 0, and we also have to simulate the result for the reactive power control. We have similar results. As you can see, we can reach the desired value in around 3 seconds. So we only change the reactive power, while the active power remains almost constant. But this is a really similar test where we indicate to the PPC that the power factor must reach different values between 1.95, and we also are reaching the values around 90% in 3 seconds. After 5 seconds, we reach the desired values. For this case, we accomplished with the regulation. So far, we don't have a lot of problems with active, reactive, and power factor for the plant. As you can see in the figure, the green line is the active power, remains constant, and the power factor is controlled changing the reactive power. Here is where we have some troubles, because according to the regulation for this plant, we have to reach these values, for example, 1.05 and 0.95. And once we try to reach these values, the power plant doesn't achieve any value, even in more seconds. We tried to perform different tests, but didn't achieve any results in the voltage control test. We are working, actually currently we're working in this specific case, but the set point values are out of the scope of the plant. I don't know how to say, but it could be related to the point where the power plant is connected and the capacity of the plant. I mean, it could be a strong load and the power plant is not big enough to help us to change the voltage at such as that capacity. And that could be a reason. Actually, the grid code could be a little more flexible about cases like this, because sometimes it's not possible for the plant. We will compare after the results with the real test, but we are expecting that the plant won't achieve the desired results. So we will have to explain to Senase why the plant didn't achieve these values, and that's another challenge. Well, also the frequency deviations. During the execution of this, we have to down the active power to the 8%. So for this case, we have almost already around 64 megawatts in order to have enough power to increase or decrease to impact the frequency of the system in that exact point. So between some values, we don't change anything because the frequency is around the value. But if we detect some changes, the power plant must be able to change the frequency in that exact point. But in this specific test, we have 30 seconds to reach the value. For these simulations, we only have 20 seconds, for the reason I already explained. Here also we have an example of frequency test, and also we have 20 seconds around 20 seconds of simulation, but from the regulation we actually have 30 seconds to reach that value. And that's it for the example I have to present here. Thank you for your attention.